So I recently finished building this alternator powered bicycle. A few years ago I uploaded a video titled Converting a Car Alternator into a Go-Kart Motor, and that video sort of just blew up. It became the most viewed video on my channel, and still to this day there's a lot of interest in it and I still get many questions about it. So I think it's about time I revisit the alternator motor. But before I get into things, if you're new here and you haven't seen my other video on the alternator, then you may be wondering how an alternator can even be converted into a motor. I'll go over this briefly, but if you want to see step by step how I converted this alternator, then you should definitely go check out that video. I'm literally just picking up where I left off. So as I mentioned in my other video, an alternator is really just a three-phase motor with a three-phase rectifier to output direct current. So let's say you have an alternator and you want to convert it into a motor. Basically all you want to do is open up the alternator and remove the diode pack. So looking at this diagram, you want to cut the stator windings loose from the diode pack and then attach your motor leads. You'll need to keep the brush assembly in order to apply a voltage to the rotor windings. Here I have a small brushless motor in DSC. The converted alternator works the same way as the brushless motor, only there's one difference, and that is the brushless motor's rotor consists of permanent magnets and the alternator's rotor is an electromagnet, which is why it needs a voltage applied to it. Here you can see I'm controlling the brushless motor with a servo tester. If I hook up the alternator in place of the brushless motor and apply a voltage to the field, you can see it operates the same way. Also, if you want to reverse the direction of the motor, all you need to do is swap any of the two phases. So I have my converted motor and now I want to install it onto a bicycle. I decided to use Old Rusty for this build because it already has the battery mount on the back, which will save me some time and just make things easier. The original plan was to control the motor with this Kelly KSL controller. This is a programmable sensorless controller with a high current limit, and I thought that it would work perfect for this project. But things didn't really go as planned because when the controller is powered on, it performs a startup sequence and then without touching the throttle, continuously drives the motor at a low RPM. I spent way too much time playing with the parameters trying to get the motor to stop spinning, but had no luck. So I eventually reached out to customer support and this is what they told me. Number one, this controller is not suitable for EVs, and number two, the controller will drive the motor with a certain low speed once it's powered on. You cannot stop the motor unless the power is off. In other words, I didn't do enough research and basically wasted my money on this. But I wasn't going to give up there. I was determined to make it work. I mean, other than the controller spinning the motor at a low RPM when powered on, it still worked as it should. And I'm sure that this is the only reason that these controllers are considered not suitable for electric vehicles. So this is when I got the idea of using a centrifugal clutch. I know, you're probably thinking, how ridiculous, an alternator converted into a motor with a centrifugal clutch. Well, I just had to try it. Okay, Old Rusty version 2, test number 1. So this is the startup sequence. And there we go. All right, here we go. I mean, it's got terrible starting torque and the clutch is slipping non-stop, but once I get going, it's actually not bad. And the motor's still completely cold, so that's a good sign. Yeah, so if I don't help it out at the start, it takes a while to get me going. So right now I'm just pedaling, but once I start up the motor, it sounds horrific and the clutch slips non-stop. I mean, other than this horrific noise, it's not bad. I feel like I'm going pretty fast here. So in conclusion, Old Rusty version 2 went at top speed of 37 kilometers per hour, and it has a very noisy clutch. Not gonna lie, these weren't really the results that I was hoping for, and in general, I would rather not have a clutch on an electric bike. But I already have this programmable sensored controller lying around from some previous projects, so I'm thinking I'll try installing sensors into the motor. Both of these controllers even have the mounting holes in the same spot, so that's a bonus. This is a Hall effect sensor. Hall sensors are a type of magnetic sensor, and they detect the presence of a magnetic field. They add capability for both higher starting torque and higher RPM. Bipolar latching Hall effect sensors are used in brushless DC motors to determine the actual location of the rotor relative to the stator. The most helpful article that I came across on the theory of Hall effect sensor placement was posted by a man named Jed Story. I'm not going to get in all the details here because this is a confusing topic and not the easiest to explain in a clear way. So if you would like to learn more on this theory, I have placed a link to the article in the description below. Most controllers expect Hall effect sensors to be placed either 60 and or 120 electrical degrees apart. The controller that I'm using can work with either, but I'm going to go with 120 degree spacing. The first thing you want to find is the number of mechanical degrees that the rotor spins to make one complete electrical rotation. Mechanical degrees in a motor refers to the rotation of the shaft. One revolution of the shaft equals 360 mechanical degrees. Electrical degrees in a motor has to do with the magnetic position of the rotor. One transition from north to south to north again equals 360 electrical degrees. My alternator has 6 pole pairs, which gives us 60 mechanical degrees per 360 electrical degrees. Since we want 120 degree placement, we need to divide our equation by 3, which gives us 20 mechanical degrees per 120 electrical degrees. So to visualize this better, I busted out the geometry kit and drew a circle the same size as the inner diameter of the stator. I then used my protractor to mark the 20 degree spacing and could see that the sensors need to be placed exactly 2 slots apart. The article that I mentioned earlier also provides formulas to determine the number of mechanical degrees per slot and number of slots between Hall effect sensors, so you don't need to draw it out like I did, but I thought it would be better to show this diagrammatically. I temporarily installed the sensors into the ends of the stator slots with hot glue and fishing line like so. There are a total of 36 wiring combinations for the Hall/phase combination between the controller and the motor. Only 2 combinations are correct. One drives the motor clockwise while the other drives it counterclockwise. So I tried all 36 wiring combinations and none worked. A couple of the combinations seemed like they wanted to work, but the controller would lose signal shortly after holding down the throttle. So I assumed maybe my math was wrong on the spacing, or maybe a sensor had gone bad, so I found the schematic for a Hall sensor test gadget on a forum. After making it and testing the sensors, I could see that all the sensors were functioning correctly. When a south pole passes a sensor, it turns the LED on, and when a north pole passes a sensor, it turns the LED off. So now that I knew the sensors were functioning properly, I was convinced that my math on the spacing must have been incorrect. So I tried spacing the sensors differently and still had no luck. I even tried a different controller and that didn't work either. It got to the point where I just threw the math out the window and randomly started placing the sensors, which obviously was a terrible idea and didn't work. This became exhausting, so I decided to take a step back to more closely examine what the problem could be. I eventually thought that maybe this isn't an electrical problem and maybe it's a mechanical problem, and that's when it hit me. Brushless DC motors use permanent magnets, which are almost always rectangular in shape. But the rotor of my alternator is an electromagnet and has these crazy spike-shaped poles. So when the sensors are placed at the edge of the stator slots, the distance across the poles is uneven and therefore why the controller loses signal. So I decided to install the sensors directly in the middle of the stator slots with my original 2-slot spacing. I removed the top layer of the insulation paper and then covered the windings in epoxy before installing the sensors. And finally, after finding the correct wiring combination, this worked. What a relief this was. The final step was to install the sensors permanently into the motor with epoxy and then clean up the wiring. This is what the LEDs look like when I rotate the motor shaft with the correct sensor placement. The Hall sensors output either a 1 or a 0, and with 3 sensors we can detect 6 different states. The sensor values are determined immediately following any transition from high to low or from low to high, and with the correct spacing the sensor outputs are never all high, 1, 1, 1, or all low, 0, 0, 0 at the same time. So that concludes my crash course on Hall sensors. Now let's finally go install this motor back on the old Rusty and see how it performs. Is that weird?
No, it looks perfect.
There we go. It's done.
Something about you, just something about you lately, yeah. No, I don't care till she gets in. Holding out for a while, different affection, just a different affection lately, yeah. No, I don't care when she gets in. I'm pulling into your smile. I'm pulling into your smile. I'm pulling into your turn back time, they'll tell there's something. It all comes, then it fades to nothing. Turn back time, they'll tell there's something. It all comes, then it fades to.
So the Hall sensors have made a world of difference, and this thing performs far better than I had originally envisioned. So far it's had no problems at all, and it's pretty quick too. So let's go see just how fast it can go. That's right, got old Rusty up to 69 kilometers per hour. Not bad for a $20 alternator and a sketchy old bicycle. Honestly, I think I could get this thing to go even quicker, but I have no interest in going any faster on this thing. I don't think this bike was meant for such high speeds. Also, I know old Rusty isn't the prettiest, but I'm just keeping it true to its name. Overall, the performance has far exceeded my expectations, and I can ride around non-stop with the motor only getting slightly warm. On a full charge, the longest I was able to ride was just over 30 minutes with only a few short stops. And that's with my 48 volt 18 amp hour battery. The field is powered by a 12 volt LiPo battery. I think it would be really cool to make a permanent magnet rotor for this thing and turn it into a brushless motor, so maybe you'll be seeing that in the near future. But I think I'm going to end this video here. This project was a ton of work and I really hope you all enjoyed it. So thank you all for watching, and I'll see you next time.